Welcome back. In this video, we'll be proving the result about sums of geometric series. So let me show you the result. First, we actually used it in the last two examples. It tells us that the sum of the partial sums are equal to first minus first missing over 1 minus ratio, and it tells us that the series equals the first 1 minus ratio if r is between minus 1 and 1. All right, so we'll prove this. The proof is really nice. That's part of the reason I want to show it to you. So let's prove the finite version first. One thing that we'll need is the fact that the terms an are equal to a first term and then ratio to the n minus 1. All right, here's how we'll do it. We'll start looking at the sum. All right, the sum is a1, so a2, which is AR, A3, AR squared, and then it keeps adding up. And then we have, let's use a couple terms in the end, R minus 2, AR, and minus 1. All right, what I'm going to do is I'm going to multiply S by R. So I'm going to get RS, and that's going to multiply each of the term by R. So I'll get AR instead of A. I'll get AR squared instead of AR, and so on. And then let me write, and we'll have AR n minus 1 here, and then AR n for that one. So you can see that a lot of terms are in common, and so I want to use that to my advantage. I'm going to subtract the two. So I'm going to take S minus RS. Last time that we proved something like that, it was like the sum of integers thing, and we actually flipped it and added them. It's a similar story here. It's actually quite nice. So if I subtract them, let's see, these cancel. So let me write them. So we get A plus AR squared plus AR n minus 2 plus AR n minus 1. And then I'm going to subtract AR squared, and I'm going to subtract AR n minus 1, and I'm going to subtract AR n. All right, let me not write this one. Let me put it in the 3 dots. It's going to make it cleaner. I mean, it's right anyways. It's just that I would need an extra term. And so if you actually look at what cancels, the AR is gone, AR squared is gone, and this one is gone, and I'm only left with 2 terms. I have A minus AR to the n. So if I factor the S out, I get that the sum times 1 minus R is A minus ARN. And so the sum itself is A minus A to the Rn over 1 minus R. And so A is A1, AR to the n. Using this, we need to increase by 1, and so AN plus 1, and then 1 minus R. Works perfectly. All right, now let's try to take a limit of this. So summation, we're looking k equals 1 to infinity of an. That's going to be the limit as n goes to the positive infinity. If I sum up to n of ak, and we just found what that was a second ago. If I sum up to n, I'm going to get exactly this right here. So I'm going to get a minus arn, 1 minus r, and then I need to take n to be infinity. That's the only term that's going to matter. So what I'm going to get is a minus a limit as n goes to positive infinity r to the n, 1 minus r. This actually goes to 0 if r is between minus 1 and 1. Right? If I multiply 1/2 by itself, this is going to go to 0. If it's not between minus 1 and 1, it won't go to 0, and so the whole limit will not converge. In fact, it won't converge at all. And so here I'm going to get a minus 0 over 1 minus r. I'm going to get a over 1 minus r. There you go. All right, so let me say this is the end of this section. The next section is about annuities, and so we'll be looking at an application of all of this to money.